I am very happy to start the new series of seminar with this room variety of people very interested in the seminar in general, and of course about the discovery of Proxima B. I think that this may have influence in the institute that the people during the summer we were very excited about the discovery, and we didn't understand. I mean, for people like me that come from galactic groups, I didn't understand properly what was going on, but of course everybody read the nature and said, my God, Pedro Amado is in the red. It's very nice that they participate. Okay, but the people from the institute participate in this big discovery that may produce some chance in the future of this kind of research. Now I want to do some practical information for new students. You have to sign this piece of paper in order that I can make some certificate afterwards. And now I shall say some words about Pedro. Amado, most of you know Pedro, but I will give some information about his career, his past career, and of course with you a really wonderful future career. Well, hopefully we expect that pretty soon or later you will become a staff member of the institute, and we will be very proud of that. While in the past he has been traveling a lot. He started his career working in the observatory, and then the University of Belfast. Then he went to Italy, Catania, and then came to the institute. And after a few years in the institute, he went to work at ISO as a postdoc fellow. And then he came back to the institute with the Ramon fellowship. But and from that, I like also to say that we appreciate very much from the point of view of the institute that he has been the leader of the Carmenes project that most of you know, that is very important for Galacto. Thank you, Pedro, for this wonderful project, and also for to cover the deadline that we have, that was January 2007. Everybody was very worried about this day, and unfortunately you got so that I am very proud. that you are here and that you work so hard to get this successful instrument that I suppose it will play a big role in the future of the extraplanetary research. So I am so that now, Pedro, I will leave the word Pedro, and I want to inform all of you. I sent an email that we will have a seminar, a normal seminar, and afterwards Pedro wants to make a taller inside the institute. So for those of you that are interested in Proxima B, just stay in the room, and we will have this taller. Okay? Thank you.
Okay, well, thank you, Pepa, for those very nice, very kind words. I appreciate it very much. Okay, this is the title of my talk today. Actually, I didn't know which title could be best for this talk, and I said, well, I don't know what I'm going to tell these people about Proxima. They don't know already, and then the title stuck there, so I left it. I am here representing the Pale Red Dot collaboration. This Pale Red Dot collaboration that discovered this exoplanet, and I will tell you a little bit more about this collaboration in a few minutes. But the talk in general will cover a little bit of why we are searching for extrasolar planets around these red, cool, active M dwarfs. I will talk, of course, a little bit of, well, the context, how it came to be that we here at the IEA are working in this research line, and why we built Carmenes, and why we are leading Carmenes and other projects, other surveys for looking for extrasolar planets. I will get more deeply into the Pale Red Dot campaign. I will talk about Proxima B, and this sort of workshop, or well, it's like a discussion of what could come next after all this. I will tell you now. So, the main question: why we are looking for exoplanets around M dwarfs? There are a few obvious reasons for this. The main one is that they are very numerous. They represent 70% of the stars in our galaxy. They are our closest neighbors. Proxima Centauri is an M dwarf, and it's the closest star to the solar system. And here, I show part of the volume around the solar system, and many of the small red dots that you see here are M dwarfs. This is a volume that extends up to 20 light years around the solar system. They live longer, so for any planet that could be orbiting these stars, they will have more time to develop life on their surfaces, and they are smaller and cooler, and that means that they increase the chances for detecting these exoplanets orbiting around them, especially if they orbit in the habitable zone of the star. So this is basically the last two reasons are because the techniques we use. We detect easily planets orbiting small stars rather than larger stars like the Sun or even larger. We know that Earth are orbiting around the Sun have an effect on in radial velocities. That is one of the techniques we use for detecting exoplanets of only 10 centimeters per second, while orbiting M dwarfs, this amplitude can reach 1 meter per second. Okay, these M dwarfs have been recognized for all these reasons in probably all the how do you call them? I don't remember the name now. Well, in all the reports made by the community, that these are like a short, the best way to find exoplanets in the habitable zone, habitable planets around these stars. This is known that this was possible with visible spectrographs, but for the coolest stars, it was realized also that the need of near-infrared spectrographs was something that would be needed for detecting these exoplanets. And this is why we started thinking about building Carmenes. Carmenes is a near-infrared high-resolution spectrograph together with a visible spectrograph that is now installed at the Clark Observatory. And the building of this instrument came from the interests of several groups, several communities in Spain in particular. We gathered the interest of the exoplanet community that wanted to contribute to this successful career of detections and confirmation of thousands of exoplanets. We gathered also the interest of the astroseismic community because we were also trying to understand pulsations in the stars, and we wanted a long wavelength coverage, extending the coverage in high resolution spectrographs from the optical range to the visible range. So all this came into be, and at the previous workshop for Calalto we presented Carmenes, which has these main objectives: to detect terrestrial planets in the habitable zone around M-type dwarfs and study the formation of planets around these M stars. As secondary objectives, or as additional objectives, we want to understand activity, magnetic activity in these stars, and pulsations. So the niche for the exoplanet research with Carmenes was then, and it still is, basically unexplored. These are planets. We have here the planetary mass in Earth masses, and we have here the host star mass in Sun masses. So this is the region that will be covered, or the region for which Carmenes is optimized for the coolest small mass stars, M dwarfs. And as you can see, well, there are many objects here, but these are planetary masses determined mainly from photometry. When you get the planetary masses from radial velocities, and then you start having less objects here. And then when you try to have objects with both masses, precise masses, and radii determined, you have only, at least by then, only one object. And by then I mean July this year. But the field goes so quickly that this may have changed in the past months. Actually, it has. But anyway, we need to cover, we need to fill this region between the 1 and 10 Earth masses planets orbiting M dwarfs to understand how they form and how they evolve. Well, Carmenes, in principle, will detect all the planets with masses between 1 and 10 Earth masses in the habitable zone and below of M stars, and it is optimized to observe these red objects because of this near-infrared spectrograph, which covers from 1 micron to 1.7 microns. So it covers the peak where the peak of these stars in the flux of these stars. So you can compare the visible spectrographs that are already running and observing the region they covered here as compared with the region that Carmen's covered in a single shot. So this is a technical advantage of Carmen's with respect to other instruments. But also we are involved, well actually we co-lead other surveys for searching for exoplanets around M dwarfs, and this is one of them. This is project Cool Tiny Bits, which make use of the synergies between these three science cases that I have already told you about. The study of pulsations around M dwarfs, in M dwarfs, the detection of compact planetary systems around these stars, and the study of magnetic activity, to put observing proposals to two of the, basically they are the only or the most precise instruments currently providing radio velocities, which are HARPS at La Silla and HARPS North at TNG in La Palma. So with the data we collected within this project for Proxima Centauri from La Silla, and with previous data that we had already from other instruments, less precise data but anyway useful, like Jueves at the VLT, we were starting to see some hints of a signal in this data previous to our pale red dot observations, and this was the driver to organize this pale red dot project, this pale red dot campaign, which is formed by 31 scientists from 8 different countries. And well, as I say, it was set in a way to try to solve all the problems with the previous data we already have. It was especially optimized and designed to observe Proxima Centauri in search for or trying to confirm the signal that we were already seeing as a hint in those previous data. So we started to observe Proxima Centauri, and this is the pale red dot team here at the IAA. So we were collaborating in several ways in this project, which, as I say, was observing Proxima Centauri, which you already know where it is in the southern hemisphere, in the Centaurus. What do you say? Okay, in the sky where the Centaurus is, and it seems to be the three stars Alpha Centauri A and B and C seems to form a system of stars, but this is not shown yet. So Proxima could be part of this system or not. And they are 4.2 light years away, or 1.3 parsecs. These are two images of Hubble, which, well, doesn't say much, but they say that these are the best images of this Proxima Centauri here. And from those pre-pale red dot campaign data, which were this data coming from the UVES survey of M dwarfs that started in 2000 and last until 2008, collecting 232 data points, and the survey by the Geneva team with the HARPS La Silla spectrograph, which collected 264 data points, together with our Cool Tiny Bit survey with HARPS, which included also some high cadence observations. All these, as I say, gave us an indication that there was something in the periodograms of the data set. You can see here a peak coming up at it is not confirmed there. You have 3 levels of significance here. This is the 0.1%, this is 1, and this is 10, and it should go over this this line. Furthermore, we were not sure that this solution was unique. We had several possibilities for this period, and also we were not completely sure that this signal was coming from the presence of an exoplanet orbiting the star, but it could also be that the star, the activity in the star was producing some kind of fake signal that was that could be mistaken by a planet orbiting the star. So then we took the pale red dot data, and with those data alone, these 54 points taken between January and March this year, we again saw the same peak at the same periodicity, which was statistically significant. However, that these 2 peaks coincide in the period is not sufficient to say that this comes from the same physical phenomenon, and that this phenomenon is a planet orbiting the star. If you put all together, all these data sets together, then you can see a huge increase in the significance of the signal, which means that not only the periodicity, but the phase and the amplitude of the signal is coherent in the 16 years of observations that we have collected and put together. So, even so, and to be even more sure that the signal was not being made up by the star, we acquired photometry for the star, quasi-simultaneous photometry during our pale red dot campaign, and we measured different indices in the spectral lines of the star to check whether the magnetic activity of the star was producing this. And then we analyzed this time series again, and we could conclude that the photometry varies, but with a periodicity which was in our data of around 80 days. And very recently, the rotational period of the star has been confirmed to be 83 days. So this goes with the rotation of the star. Then one of the indices of this, we compute from the spectral lines, the second order moment, was varying almost identically with the photometry. We saw also, or we didn't see any variability of the activity indices given by some of the proxies of magnetic proxies in our spectrum, like H alpha or calcium 2 H and K. And we didn't see any correlation between radial velocities and these activity indices when we analyzed the data. Finally, flares that are happening quite often in this star have little effect on the radial velocities. So we were not concerned about the star flaring. So since the analysis of all this activity data failed to identify any stellar activity feature that could produce this spurious or a Doppler signal, a spurious Doppler signal at 11.2 days, then we concluded that the variability in the data was best explained by the presence of an orbiting planet around the star that we named Proxima b. And with the data we had, with the Doppler technique, the radial velocity technique, you can derive a minimum mass that was of 1.3 Earth masses and the orbital distance and from this distance you can know how much flux the planet is being hit with, and compute an equilibrium temperature for the planet. This is the full table from the paper, where we give other details. And well, I will try to show you a little movie, because movies are always nice. But with this, I will explain that, as I say, the orbital distance of the planet is of 5% of an AU, 0.05 AUs, so well within the orbit of Mercury around our Sun. At that distance, and considering the amount of flux that is receiving from the star, the planet is well within the habitable zone around this type of stars. And this, the equilibrium temperature on the surface of this planet should be around minus 40 degrees centigrade, which well, is of the order of what Earth would have if it didn't have an atmosphere. So, well, in principle, it is possible that there is liquid water on the surface of the planet. Now, again, these are the facts, right? The facts about what we know about the planet is a period of 11.2 days, a minimum mass of 1.3 Earth masses, and the distance at which orbits the star. This is a comparison between the habitable zone, or the orbit of Proxima b, and the orbit of Mercury around the Sun, and of the two stars. This is some data about Proxima Centauri. But okay, these are the facts. But what else do the models tell us about Proxima b in particular? Well, we already know from other surveys, and especially from Kepler, that that exoplanets in general have a curve when you plot them versus when you plot the radii of the planet with density, that you change from rocky to volatile rich planets at 1.5 Earth radii, right? A planet with this radius corresponds to a planet that has 6 Earth masses, if we assume an Earth-like composition. So Proxima's minimum mass is 1.3 Earth masses. So it is we have around 98% chance that Proxima b has an actual mass that is smaller than 6 Earth masses. So from the current knowledge that we have from these planets and how they form, we can say that Proxima b is likely to have a solid surface. Okay, even if a magnetic field is not needed for a planet to maintain an atmosphere, and I think Venus is an example of this, this is a very good shield from the magnetic activity of the star, in particular from Proxima Cen, that is an active star, and the planet is much closer to the star. So models currently say that 50% of Proxima b analogs, planets that are similar in characteristics of what we can see for Proxima b, develop a magnetic field that lasts until today, or for longer than the age of the star. This is a work by Zuluaga and Bustamante this year, and that a planet with chondritic abundances may not generate a magnetic field, but all other models do maintain a magnetic field, by Burns et al. In 2006. In general, it is probable that Proxima b may generate and maintain a magnetic field. What about its atmosphere and other issues like liquid water on the surface? Well, again, models show that if you have an incident stellar flux on the planet which is small, you require less heat transport and therefore a less massive atmosphere to balance the atmosphere when you have a synchronously rotating planet. And this means that you have one of the hemispheres irradiated all the time by each star and the other hemisphere frozen, okay, and looking away from the star. So what this also this paper by Goldblatt 2006 show and the result from this is that the low Proxima Centauri b incident flux may help enhancing habitability if it has suffered some atmospheric loss or begun with a low volatile inventory. If you have cases which are not so favorable, then this lower incident flux from Proxima can help keep maintaining habitability in Proxima b. Okay, Turbet et al. In 2006 again. Well, these are papers that just came out from after the publication of the discovery of Proxima b. So they find from 3D global climate models, and if they take into account the two likely rotation modes for the planet. One is the one I have already explained, one-to-one resonance, and another one is the 3-to-1 resonance. And if they vary the surface water inventory and the greenhouse effects, which are not known, this is one of the largest unknowns that you have to run these models. Well, then the result is that a broad range of realistic atmospheric composition can allow surface liquid water on this planet, and that despite the magnetic activity on Proxima Cen, Proxima b is a viable candidate habitable planet according to Rivas et al. What do the models tell us about the formation scenarios of these planets around these M dwarfs? Well, from Coleman et al., I get these four different formation scenarios that produce these results. If you have in situ formation via giant impacts from a locally denser disk of planetary embryos and planetesimal, you get Proxima b analogs with a moderate content of water and volatiles. If you have multiple embryos forming, migrating, and then colliding to form the planet within a gaseous protoplanetary disk, then you have the result from this is that you get in the simulations multiple ocean planets. If a single accreting embryo forms at large distances from the star and then migrates inwards, accreting everything that it finds on its way, you can have the result is a single ocean planet. And if you have people accretion but interior to the snow line in the system, then you have a dry planet on a circular orbit. And Barnes et al. Says that if planet B, if Proxima b formed in situ in the place where it is found today, while runaway greenhouses during the time of the contraction of the star may have completely desiccated the planet, or produce an atmosphere that is not good for having for having it habitable. Right? So, concluding, we have Proxima b as our closest extrasolar planet neighbor. This is an opportunity, and we think that it's a unique opportunity to understand how planets form around these stars, because it is so close, and we can already start using several instruments to confirm or refute these models, or at least put some constraints on the models. And also, being the closest one, we know now that several projects are trying to reach this system by space probes. And one of them is the Breakthrough Starshot project. Probably you have already heard about it. It was funded this year, also in April, on the 12th of April this year. And it was funded by Yuri Milner and Stephen Hawking, with some starting funds to try to develop the technology that it is needed to send these probes to the system. Right, so as I said, this is the current board of this initiative, which is trying to send these probes to the system. It will be these probes will be very, very light in weight. Probably, I'm not sure that you can see the sketch of what is supposed to be one of these probes, but they will be attached to large sort of sails or wings or something like that, will be pushed with laser beams from Earth to accelerate it to 1/5 of the speed of light. And there you can see the little small probe on the sails. And with this luminic propulsion, they intend to send a fleet of different probes at different times, so that you can find this swarm of probes reaching from Earth to the system. And basically, well, this is the end of my talk. I hope that I have told you something that you didn't know before, and thank you very much.
Thank you, Pedro. And now you have the opportunity to ask questions. Even I have a question through internet from somebody that was watching the streaming. Well, I am not going to translate into English because it takes me longer. The question is the following. La detección de Próxima Centauri B indica que la masa mínima es 1.3, la masa de la Tierra. O sea, la medición ha sido de m por el seno de la inclinación, que va de 1,3 veces la masa de la Tierra para seno de igual a 1 hasta mínimo 4 veces la masa de la Tierra, límite superior de la masa para un rango de 80% de inclinaciones posibles en sistema exoplanetario y ser un gigante gaseoso helado. ¿Por qué se descarta o no discute el caso de máxima masa para el planeta? ¿Hay algo que realmente no haga viable un planeta con estas características orbitales y esa masa gaseosa alrededor de Próxima Centauri?
Do you have to translate it? Or?
No.
Or I just answer. Okay, well, the question is, yeah, we have a minimum mass for the planet. We don't have the absolute mass. This will come next, hopefully. So, why this planet is rocky and is not of larger mass? I think I have answered actually the question in one of my slides. I will put it back again. Actually, from what we know, in particular from Kepler, there is a break in the function that describes the distribution of exoplanets with mass and radii, and this break is at 1.5 radii. So, okay, if we assume this Earth-like composition, then this limits the mass to 6 Earth masses. And as Luisa says, the mass of the planet is probably between 1.3 and 4 Earth masses. So this is well in this region where we think that if an exoplanet is, then it has to have an Earth-like composition, or at least a rocky core that can have this solid surface. I'm not sure if this answers Luisa's question, but at least summarizing from what we know, especially from Kepler, this planet is probable that has a solid surface.
Thank you. Rainer?
So, I was stuck 10 years ago, I think, in things called exoplanets, and I remember that M dwarfs were never considered good targets because, I mean, they're frequent, but then we have answered a lot of these questions that apparently now the solar wind is not so much of a problem because the planets may actually have stable magnetic fields for the lifetime of the universe. Apparently now the tidal lock isn't a problem. Is that a problem or not for the atmospheres? But in principle you say you can have warm atmospheres and place with liquid water. So the third thing that I remember that was discussed with M dwarfs are X-ray flares that could sterilize the planet. Is that a problem, or is that some old stuff that we shouldn't worry about now?
Well,
are they active and non-active dwarfs?
Yeah, I think more than the X-rays is the extreme ultraviolet flux, which is dangerous for the atmosphere of the planet. In particular for Proxima b, as far as I know, I'm not an expert, but from what the papers say, this is in certain conditions is not a problem. It's not a problem. It is true that the planet has been exposed to larger fluxes in the past because, well, Proxima is 4.8 giga-years old. When it was younger, probably not. For sure, it was more active, and this is a problem if you have a planet forming in situ and trying to keep an atmosphere. But well, one of the scenarios is that the planet form farther out and then migrates inside, and this putting some distance between the star and the planet helps. Also, the formation of a magnetic field also can help shielding the planet and its atmosphere from the radiation, from the flux from the extreme ultraviolet radiation.
Magnetic field
Of the planet.
But from the ultraviolet radiation.
Well, no, in general, from the particles of the wind, from all the incident radiation at wavelengths that are not good for keeping the atmosphere and for keeping for being beneficial for habitability for the planet in general. Either particles, high energy particles from the wind, this X-ray or extreme ultraviolet radiation, whatever. All these different scenarios at least don't exclude that the planet can have an atmosphere and can have liquid water on the surface.
Do you have any indication for any further planets there? For example, for migration, it would be very interesting to see whether there's far out some giant planet or something.
Well, there is.
Embargo.
No, but it's not. We cannot exclude that some of the signals we see at longer periods may be due to other planets or to activity cycle or something, but we don't know. We see some of the signals, but could be the star or it could be planets farther out, but this needs further investigation, yes, for sure.
Enrique?
What is the difference between the PRD HARPS campaign and the previous HARPS campaign that makes it more significant, the peak?
Well, there are several differences. First, the way in which the observations were taken, or the frequency, or the distribution of observations along along time. We already had some idea of the period that we were looking for because we have some indication there. And we, with these these big surveys, like Jueves or HARP surveys, they are surveying many stars, and they are observing the stars in not a very uniform way. You can start having problems with the observing window and the periodicities that you are finding in the data, either rotationally produced or by whatever other phenomenon. And the difference with us was the first one that we took very homogeneous observations, one observation per night at the same time in the night for 2.5 months. And then also we took simultaneous observations with photometry, just to make sure that the signals we were detecting were not produced by the activity, rotation of the star, or anything produced on the star.
So, you have a huge number of M dwarfs in the galaxy. What is the relation, though? I mean, on the other hand, M dwarfs they're extremely numerous, but they're also extremely faint. So, how far out do you go in light years with the surveys that you're planning? How far can you go out? What's the numbers roughly?
Well, what I have said more or less. I think the mean distance for the Carmen surveys is around 15 parsecs. And yes, these surveys cannot go much further because then you don't have flux especially in the visible, where these instruments are optimized for. If you go to the near infrared, you have more flux and you can get a little bit fainter, but this is more or less the.
So how many targets do you have?
In Carmen we have 300 northern targets, so you can more or less assume that you will have the same amount of targets in the southern hemisphere. Well, there are quite a few that we can probe for detecting Earth-like or terrestrial-like planets around these M dwarfs.
Jaime?
Do you have any other candidate?
Of planet in Proxima?
Planet Proxima observations.
Yes. How many? Let me see. No, there are not so many. I mean, around M stars, you have to get very precise to start discovering new planets. And we have the HARPS, they are the best instruments up to now. And Carmen is working since the beginning of this year. You need a very high precision to discover the smallest planets, and I would say that basically most of them, at least those producing larger signatures, larger signals, are already discovered. But then you have many that don't produce a big signal, and the better your precision is, the more targets you will discover, that's for sure. But we have some of them. Some.
I have one question myself. Maybe it's a stupid question, but which is the next study you plan to do with Proxima B in terms of studying the proper system, the atmosphere, and how can this be done when you think that this is the nearest to the Earth, maybe with interferometry observation or something you can get much more information
Well,
on
this is
that? I
part.
don't know.
This is part of the next part of the session. So I will answer to you.
In the taller. So I
Yes.
have to stay here.
You have to stay if you want to. If you want to
I
answer
am
for
very
that.
glad that
Very good.
I
Thank
asked
you.
that
I'm glad that you're
question
glad.
to you. Okay, so then we will finish here for the seminar for the most interested people in this question. This is what we didn't prepare that question
No.
before.
No, I am.
So that for the people that are interested in what is
I
going
know
to
that you-
happen with Proxima B, so you can stay here and we have a long discussion on that. Thank you.